This lesson is for FST lesson 9.6 on solving exponential equations. What we're going to be doing today is finding a missing exponent using logs and using algebra. Typically the question is either going to start out as log of another base of a number equaling something. And so when you write that out in exponential form, it's base 2 in this case, raised to an unknown power equaling 3. In many instances, taking the number and raising to a power we'll be able to figure out just using trial and error. On a question like this, there's no way we can figure out on our own 2 to the what equals 3. Now, I do realize that on some calculators, in particular the Inspire calculators, you can simply write or type in log base 2 of 3. But not all calculators are Inspire calculators. Most calculators like Scientifics and TI-83s and 84s and all the Casio calculators, those all only have a log button that's base 10. So while I realize that some students do have the capability of simply typing in log base 2 of 3 and getting an answer on the calculator, we wouldn't have that capability necessarily on every calculator. So that's why we use this technique that's here in this lesson. So you're going to rewrite the problem in exponential form, and then you're going to introduce logs on both sides. So you're just going to write the word log on both sides of the balanced equation. Then there's a property of logs that we looked at in 9.5, where if you have an exponent up here that can move to the front of the log. Now that exponent can't move until a log is introduced. Some people do like to put these two steps together. They introduce a log and they move the x just to save time and space, but I wanted you to see it as a separate step here. Then to try to get x alone, we are currently multiplying it by a log of 2, so we would divide both sides by log of 2, and then we just calculate. So you type in log base 10 of 3 divided by log base 10 of 2. The logs here do not cancel because log of 3 is one number and log of 2 is another number. So the logs are not separate, they go with the number that they're next to. So typically here you'll be using a scientific calculator most likely, so you wouldn't have access to typing in log base 2. You would have to use a log base 10 to solve. And then just make sure you round appropriately. They'll have to tell you what to round to. If they don't, then you just get to round to whatever you'd like. So we're just going to do one more here just to practice. Actually, why don't you try this one on your own and I'll reveal the answer in the video here shortly. Pause the video, give it a try. So here you go. Rewrite it in exponential form. I filled in an x. If you used a different letter or a question mark for your exponent, that's perfectly fine. Then introduce a log on both sides, move the exponent to the front. If you skipped this line number 2 altogether, I'm okay with that. You could just go right from here to here. Then you should divide on both sides by log of 4 and then type that into your calculator. And if you round to the 10th, like the directions say, you should get about 3.6. So because a lot of log problems end up turning into a problem like this over and over and over again, they turned it into a theorem which you can use as a shortcut. It's called the change of base theorem. In order to use this theorem, the bases that you're working with must be the same. So when you're working with log of a base other than 10 of a number, you're basically just going to do the log of the number divided by log of the base, and then the bases have to be the same. So a lot of times people write this property as log base b of a over log base b of b. But know that it also works if you use a completely different base for both of them. So you could say log base 4 of a and log base 4 of b. The biggest thing to remember here is that the thing you're finding the log of goes on the top, and the base that you're using, you do log of that on the bottom. But the base could be just about anything. It doesn't have to be one of these two numbers. So let's just put this into practice now with the one that we just did, log base 4 of 150. That was the problem that we just did. So we did all this work to try to get down to 3.6, but if we use the change of base theorem, we can get there a lot faster. All we're going to do is say, okay, let's do log of 150 on the top and log of 4 on the bottom. Isn't that what we did? Right there, boom, that's what we did. So when you're working with solving, you can just simply use the change of base theorem from here on out. And so you would get the same answer of 3.6. It just saves you having to do all of that work. So let's finish up by talking about base E problems, and then we'll do a quick word problem to finish up today. If you're solving with a base e, you should be using a natural log. Know that you don't have to. A regular log will also work in this case, but a natural log will be the easiest when there is a base e. So if I incorporate a natural log on both sides and move the exponent to the front, I end up with question mark or x, natural log of e equals natural log of 27. So I incorporated that natural log on both sides. Keep in mind that the natural log of e is just a 1. If you try to simplify that and rewrite it in exponential form, it's natural log, so it's going to be a base e. We're raising to an unknown power and we're trying to get to this e. So e to the what is e? It has to be a 1. So if you forget that and decide to divide by both sides by natural log of e, that's not bad. It's just a step that you don't need because all you're doing there is dividing by 1. So I'll leave it there for you for those of you who like to just keep your methods the same. But know that you would get the same answer if you simply did natural log of 27. So if it's a base e, just take the natural log of the number, and whatever you get when you type that in is your answer. So in this case you get about 3.3 because we're rounding to the 10th. Let's finish up now with a word problem. I'll give you a moment to read through it and look at it. So how long would it take $10,000 to grow to 15 if it's in a savings account that pays 2.59% interest compounded continuously? How long will it take the original investment to double? So we're going to use the PERT formula because it says continuously. The original amount is the P, that's the 10,000. We're going to use the letter E on our calculator. We're going to raise to the percentage, but that percentage needs to be changed to a decimal. So we'll do 0.0259. The time we don't know, so you can either write it as an X or a T there. And we're trying to get to the number 15,000. Now we're going to be solving for x, or the exponent here. Before we can start incorporating a log on both sides, we need to isolate the base. So let's go back to our notes back here, rewrite it in exponential form, make sure that you isolate the base. So sometimes there's some algebra that you'll have to do at the beginning before you introduce the logs. So make sure the base is isolated. So in this case, that's what we have to do here. So we need to get rid of this 10,000 so that the base is all by itself. So we're going to divide both sides by 10,000. And when we do that, of course, we get a 1.5. Now we're going to introduce a natural log on both sides. And what that does for us is it moves this exponent to the front. And remember, natural log of e is just 1. So we don't really need to divide by that on both sides. So all I'm going to divide by is 0.0259. I could divide by the natural log of e as well, but it's a redundant step because all that is a 1. So I'm going to take natural log of 1.5 and divide it by 0.0259. And that'll give me the missing x, or the missing time that I'm looking for. And so in this case I end up with 16. So it would take 16 years, I guess, for it to go from 10,000 to 15,000. And so to answer the follow-up question, how long will it take for the original investment to double, you would do the same question again, excuse me, but this 15,000 would change to a 20,000. Keep in mind that you wouldn't need to substitute in 20,000, you could just start right here and just change the 1.5 to a 2 because that would be the result of doubling. So you'd get a different answer if you went ahead and figured out when it would double. Lastly, just make sure you read through book example number 3. There will be some half-life questions there. Feel free to ask for help on those during class if needed.